And the same happen when we compute the pairing of V1 with V2, this stiffness element. Then the intersection is in this area. So in this area we have to compute the integral of these functions. When we take the pairing of V1 with itself, the intersection of these two basis functions are of course the same. The intersection of the supports are the support of V1. So in this case we have to find the integral over all of this set. In order to compute these integrals, we do as follows. We make a table like this, and we divide the shaded area, the intersected area, into triangles which we call 1, 1, 2, 1, 3, 1, 4, 1, and so on. The index 1 refers to the number of the node. So we now make a table for the partial derivative of the first basis function and the other basis function which we are pairing it with. And in the first triangle we note that the partial derivative of V1 with respect to x1 is just 4. The reason for this is that the value of the basis function here is 1, here it is 0, and the length between them are 1 over 4. So when we take this this value, the value of this node point with the value here, which is 0, and divided by the length 1/4, then we obtain 4. So this is the partial derivative of V1 with respect to x1. In this triangle there is no value on the value of the partial derivative with respect to x2 is just 0, because on the line here the value of the basis function is constant, so the partial derivative must be 0 in this direction. In this triangle, the partial derivative of V1 with respect to x1 is just 0, due to the fact that this function is constant along this line at the bottom. However, the partial derivative with respect to x2 is equal to 4, because the function is increasing in the x2 direction from 0 to 1, and the length is 1/4. So we take the difference between 1 and 0 and divide it by 1/4, and therefore the partial derivative of V1 with respect to x2 is equal to 4. In this triangle we obtain that the partial derivative of V1 with respect to x1 is minus 4. This is because the function is decreasing from 1 to 0 here, and it's also decreasing from this point 1 to 0 here. So that means that the function is increasing in this direction, and we get that the partial derivative is 4. Doing the same in all the other triangles, we obtain this the rest of the table. So it's rather easy to fill it out. So by using this table, we are able to calculate the pairing of V1 with V1 in the following way. We have this integral, and we are going to compute all over this shaded area, the supported area of V1, and we split this integral into several integrals. One over this, the first over this 1, 1, second over 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. So 6 integrals we have to compute and add these together. This is what we try to symbolize here, and this is rather easy to do because the partial derivative is constant in each of these triangles, so we only have to multiply these partial derivatives, the product of them plus the product of these, with the area of the triangles. And all these triangles has area equal to 1 over 32. Why is that? That is because the length of this side is 1/4, the length of this side is 1/4, and how to compute the area of this? Well, we take this length multiplied with this length and divide the result by 2, and then we get 1 over 32. So we multiply this together with the area for all of these triangles. Start with the first, this triangle, and from the table we know the values of the partial derivatives of all these partial derivatives. Start with this. This is 4 in the first triangle. This is 0. Sorry, this is not 0. The partial derivative of these two, this is the same two numbers, and they are both 4 in this first triangle, and the partial derivatives with respect to x2 is 0. So therefore we have 0 multiplied with 0 here, and in the next triangle from this table we have that the partial derivative with respect to of v1 with respect to x1 is equal to 0. So therefore we multiply this with 0. 0.0 is 0 plus the partial derivative of v1 with respect to x2 multiplied with itself, and this is from the table equal to 4. So now we have computed the values of these products for this triangle and this triangle, and we continue in this way for all these triangles, and multiplying the results with the area 1 over 32, we obtain 4. We now compute the partial derivatives of v2, the basis function associated with the second node, then it will take exactly the same form. In this case, we index the triangles in the same way. The index is related to the number of the node, but the triangle 1 is on the same place relative to this node. So we have 1, 2, 2, 2, 3, 2, and so on. And the partial derivatives are, of course, of the same type. So when we know our pairing V1 with V2, we have to look at the intersection of these supports. And how are we going to proceed to find this pairing? Well, here we see this intersection between these two basis functions. It's this triangle, which is called I2, is exactly the same as the triangle 3, 1, which is associated with this node number. And similarly, we have this 4, 1 is the same triangle as this 6, 2 triangle. So then we go into this table. We have the table for the partial derivatives of V1 with respect to x1 and x2 here. We have the partial derivatives of the basis function V2 with respect to x1 and x2 here. So what we need to do is, when we are finding this value of A of V1, V2, which is a pairing between V1 and V2, we have to only consider this integral, the integral over the intersected area. And in this case, we only have two triangles to consider, because the integral over the rest of these triangles will be 0. So we have the area of each of these triangles is the same as before, 1 over 32, and we have the partial derivative of V1 with respect to x1 that is connected to the triangle 3, 1. 3, 1, go to the table here and see what 3, 1 gives of values. It gives -4 and 4 on the partial derivatives of V1 and with respect to x1 and x2 respectively. Moreover, in the same triangle, which is we call for the basis function V2, we call it 1, 2. Here we go to the table 1, 2 here and find the partial derivatives of this basis function with respect to x1 and x2 here, and the same for all other values. The partial derivatives of V1 here, we refer to the table concerning the triangle 3, 1 for the value of this, and similarly for the partial derivative of V2. So using these table values, we are able to find the value of this pairing. You see here in the first triangle, this triangle, the partial derivatives of these two partial derivatives are from the table -4 and 4 respectively, and the value here is 4, the value here is 0, the value here is -4, the value here is 4, the value here is 0, and the value here is -4, and multiplying this with the area, we obtain minus 1.